Hi, this is our stock price simulation presentation for Project 2 of FINA415. I'm Hannah Turner and my group members are Caleb and Luke. Our agenda is we're going to start with the aim of our presentation, and then we're going over the geometric motion models, assumptions, advantages and disadvantages. Next we're going to present our model, how it works, the features, the VBA code and the simulation interpretation, and then we'll be ending with the conclusion.
So in real life, stock prices fluctuate and are uncertain. So this is the reason why we're going to simulate. Investors, they want to weigh up risk and reward. They need to predict future trends, and so simulation is very valuable for decision making.
Our aim was to develop a model to simulate the price of a stock given its current price, expected return, volatility, and a simulation step size. The model must also fit the following criteria. Make all of the input variables so that the user can change them. The user should also be able to generate easily new price paths and create a chart to show the simulated price path for the stock and its certain and uncertain components, as well as having a clear and concise layout, ease of use, and being free from error.
The geometric Brownian motion model has 5 assumptions. The first is that stock prices are continuous in time and value. Stock price is always changing over time and can be seen at all times. Even though markets close on nights and weekends, this assumption makes modelling easier. Only current stock price is relevant for predicting future price. This follows a Markov process where the price history does not determine the future price of a stock. In other words, if a stock price performed poorly yesterday, this does not determine its future performance. The third assumption is that stocks will have a proportional return over a short period of time, which is normally distributed. The prices of stocks are log-normally distributed. This log-normal distribution is asymmetrical. It has a minimum value of 0 and a maximum value of infinity, reflecting the nature of stock price, which cannot be negative. The standard deviation is continuously compounding, where variability of a stock increases as the time interval increases. However, the variability is still less than the standard deviation. The last one is continuously compounded return for stock is normally distributed. The geometric Brownian motion model has several advantages. It is an appropriate model to use as its expected returns are independent of the stock price. It involves a single process. It predicts only positive values and behaves rough like real stock prices. However, there are a few limitations to the GBM model which prevent it from being completely realistic. Firstly, it assumes a constant volatility over time, whereas in reality, volatility changes over time. Secondly, the GBM model fails to reflect how real-world stock prices jump and dive due to unpredictable news. Instead, the GBM doesn't consider discontinuity.
As you can see here, we have our model with all of the separate inputs that the user can change using the form controls. These variables are initial stock price, time increment, expected return, volatility, and time period. Once the user selects Run Simulation, which is the form button shown here, the values come up underneath stock price in the certain component and the uncertain component. These are the values that we use to make our graphs, which is shown on the left. The graph is also run off the same button. As you can see there, the graph shows the relationship between simulated stock and the certain component, with the uncertain component down the bottom, showing how the values change over each period. Next. By selecting the Display Profit Loss button, a message will come up showing how much your initial price has changed, which gives you a good idea of any profit you've made.
So our simulation has several features. The first additional feature is the profit loss calculator. So as you saw before, you're able to click the button and it will tell you how much from your original initial set share price, whether it's increased or decreased, giving you a profit or loss, which tells you the earnings per share. Another feature, the buttons that we use for the input field. So this includes spin buttons, list boxes and scroll bars. These are all to make it really easy to choose which variable the data you want to put in them. And the last one we put was the command buttons. So these included the run simulation, which automatically did the graph. It didn't need a separate button for that. And the clear graph, and then also the profit loss calculator button, which pops up with an on-screen text box telling you how much profit you made or lost.
As you can see here, we have the first part of the code, which is used to create the simulation, which we use to then make the graph. At the top you can see we have to define all of the user-created variables. Next, the range, which has to be cleared each time, so it doesn't mess up the data if you want to change the number of periods. Below that shows where all the values are retrieved from. Next, if you go a bit down to where it says cells first offset, it shows where the values are put after in order to start simulation. If you go further down, you can see the equations that are used in order to create the values, which will later graph and where they are placed. So here we have the second part of the code, which is used to create the graph. As you can see at the top again, we have to define the user-created variables. The next part is quite important. You have to define the last row, which is, you can see the formula up there, so that it can be changed if the number of periods changed. Next, where it says set range, is the values that are used to make the graph. See here, uses the last row that we just explained. Next shows, you can see under charts add, shows the type of chart and the source of the data where it's from. Below that, the rest of the information that you see is basically just the axis titles and the graph title and the different variables title. And at the very bottom you can see where we've entered code so that it stays in a fixed place. The graph is going to be in the same spot every time. So the last part of the code we used is just to create the profit loss function, which is basically just a message box, but within that it's got the ability to calculate the values you need.
So this is our simulation, as you can see on the stock simulation sheet. These are our variables here, but these are the inputs that you'll use to configure how the stock simulation is going to turn out. So at our inputs, you can see we have initial stock price at 16. You can push this up, you can push this down, depending on your requirements. You can also adjust the time increment using this drop box, and that has a range from 1 to 5 or 10 days. We'll just go 1 day. Expected return, you can see there's a scroll wheel. You can just choose which percentage you want, up to 30%. We'll go 22. Same with volatility, up to 30%, you can choose a percentage and choose the time period. Once you've done this, you'll click Run Simulation. This will simultaneously do the results and the graph. As you can see, it is calculated both. If you want to clear the graph and do it again, you just click Clear Graph. So we'll just run the simulation again so you can see. And then finally we have this display profit or loss button. So that'll just pop up a command, and it'll tell you that your initial stock price changed from 13 to 13.07, giving you a total return of 7.7 cents per share owned. And that's our simulation. So in looking at how we can interpret the simulation, we found there are a couple commonalities, especially if in the input section you had made high expected returns. As expected, you would get high stock prices in general. Vice versa, low expected return would give you lower stock prices. High variability would give you large fluctuations in the data, especially in the uncertain component, which is where a lot of the volatility is added on to the equation. Whereas the certain component didn't have as much volatility, so it is much more uniform. As they go together, you can see that the simulated stock takes on the volatility. So if it was high variability that you entered, then you're likely to get large fluctuations in that simulated stock price, whereas if you had low variability, it would be a lot more flatter. And so this one we can see that there's a reasonable amount of variability, as the uncertain component varies a little bit, but not as much as you might expect if the variability was higher. So in conclusion, why are we running these simulations? Well, because stock prices are uncertain, and as an investor, you want to know how you can get the best reward for your risk. So to do this, to simulate stock prices so we could decide which stocks work better, we have used the geometric Brownian motion model. And this was used in the equation of this simulation to really simulate these stock prices. We have simulation is very useful for decision making. You can critique and make the inputs change depending on your situation, and you'll get an estimate of the stock prices that will result from that. As an investor, this would be really helpful to calibrate which stocks at which variability or